Hello, everybody. Today we continue discussion of Chapter 5, Linear Functionals and the Hahn-Banach Theorem. So today I would like to talk about some further consequences of the Hahn-Banach Theorem for norm spaces. In particular, we have this nice corollary, 19. Let X be a norm space, then for any point in this X, the norm of this point can be given as supremum over absolute values of L of X, where supremum is taken over all continuous linear functionals whose norm in the operator norm or normal function analysis of functional norm of linear functional is either smaller or equal to 1 or equal to 1 or smaller than 1 without being 1. So the first two suprema are even attained. Before we prove it, a remark. Let us just compare this thing and this thing. So this is the operator norm of a linear functional as we have defined it already somewhere in the very beginning. So the norm of linear functional is supremum over such absolute values of evaluations at points. Points are from X, from the closed open ball of radius 1 around the origin in the space. And here, something dual, so to say. So the norm of X is supremum over of the same things, but the supremum is taken over all linear functionals, continuous linear functionals. Okay, let us compare it with this. Over all linear functionals, continuous linear functionals whose norm is small or equal to 1. Okay, so let us I guess I have the proof. So let us check this identity. So let L be a continuous linear functional with the norm small or equal to 1. Then we have absolute value of L of X is smaller or equal than the norm of L in the space of linear functionals, continuous linear functionals, times the norm of X in X. This we have discussed when we have just introduced the operator norm, in particular the norm of linear functional. So actually the norm is the smallest constant such that this inequality holds for all x's. The smallest, I mean the infimum over all constants satisfying this inequality. So since our linear functional is assumed to have the norm small equal to 1, then all this stuff is smaller or equal than just the norm of X. So we have this inequality that the norm of X is bigger or equal than this, and hence it is bigger or equal than supremum over all such L's. And hence we have shown this not identity, but first inequality. But we also have a corollary. By corollary, it was corollary 513. I guess this corollary should be here. Yes. So for any point which is not 0, there exists a linear functional such that the norm of L evaluated at this point is just the norm of x0, and the norm of L is 1. So we can take any point in the unit ball, let's say. So how we are going to use it? Let us see. So we have seen that this inequality holds, but then by corollary 513, there is L satisfying this condition such that L at a fixed point x is exactly the norm of x. So even identity. By corollary, we have here identity. Okay? Agree?
Okay.
Yes, perfect. So we have shown this identity. So here supremum is taken over a smaller set. So here we have this condition, here we have this condition. So this supremum is smaller or equal than this supremum. But again, by corollary 513. So once again, corollary 513, here we have exactly this identity. So we have even identity here. So this supremum is not bigger than this supremum, but also by corollary 513, this supremum is not smaller than this supremum. Okay, and here we have the supremum over an open ball, a unit ball, and here supremum over the closure of this unit ball. So again, due to continuity of linear functionals, which we consider, these supremums are equal. So I'm not going to write down anything concerning it. I hope that everything is clear. Do you have any questions or comments?
No question.
Perfect. Then let us go further. Corollary. So concerning this first two suprema, which are attained exactly by this corollary, because the unit sphere, it is exactly the place where the supremum is attained. Okay, oops, sorry. So corollary 521, so let X be a norm space, U be a closed subspace. X0 is an element which is not in U. Then there exists a continuous linear functional on X such that L restricted to U is just 0, but L at the point X0, which is not in U, is not 0. So let us prove it. So in a sense, there exists a continuous linear function which separates a closed subspace and a point, which is not in this closed subspace. Okay, so let us prove it. So proof. Let Q be the mapping which maps X into quotient space. So be the quotient mapping. That is, each element of X is mapped onto its class of equivalence given by a closed subspace U. Then Q of U is equal to 0 for any U in this vector subspace. So the whole vector subspace U is a class of equivalence of the region. And Q of X0 is not 0 because X0 is not in U. Moreover, this mapping Q is a bounded linear operator from this space into this space. Yes, so we have not discussed, but of course, if we have a norm space X, then we can produce a norm here, and so this factor space or quotient space it appears, so it turns into a norm space as well. So we have a linear operator between two norm spaces, and one can check that this is a bounded linear operator and hence continuous. Okay, further choose L tilde, a continuous linear functional on this space. We can take such linear functional satisfying condition that L tilde at the point, at the point Q of x0 is not 0. So such L tilde exists by corollary 513, which we have already seen. So let me show it once again. So corollary 513, for any point in some norm space, there exists a continuous linear functional such that L evaluated at this point is a given number, not 0. Okay, so hence we can construct such L. And then we may consider the functional L, which is defined as a composition L tilde and Q. And then this is the mapping from X to K. And this is the desired linear functional. So L is linear because it's a composition of two linear things. And L is continuous because it is a composition of two continuous things. That's why it is exactly what we want. And since we have this, we have also this. As well as since we have this, we have also this. That's it. Everything is clear, or are there any questions?
Nice proof. And I have a question about actually I don't remember the norm of the quotient space. Sorry. I mean
I also don't remember, but let me if you wish to know right now, let me look at. So in the book of Bogachev, there is this. Let me check. Okay, so we have a norm space, closed. It's closed linear subspace. Then a factor space, which consists of class of equivalences. So the classes of equivalences look as follows. So that is it is x plus u. X is just some point in X, yeah? So how we define the norm? So the norm, where should I write down? Let me take another color. So norm of this class of equivalences in this factor space is defined as follows. It's infimum over all norm Z, such that Z belongs to this class of equivalence. And then one has to show, of course, that this is the norm and everything is fine. So it is an exercise. But this you can read in the book of Bogachev, which is the main source of literature in this course. Okay.
I see. Thank you. Thank you.
Welcome. Okay. So let us go further. Corollary 22. Let X be a norm space, U be a subspace. Now not necessarily closed. So this closeness was exactly in order to obtain this guy to be a normed space. So in this construction, to make this guy to be a norm space, one assumes that the U is a closed subspace. So this is where it is important. So let me specify that this closed subspace is used, so to say, here. Namely, is used in the fact that this guy is a norm space. Okay, so 22, let X be a norm space, U just a subspace. Then the following statements are equivalent. First statement, this U is a dense subset in X. And the second statement, from the condition that we have a continuous linear functional L on X, such that it is restricted, its restriction to U is identically 0. This assumption implies that L is identically 0. Okay. So let us again prove is that if we have 1, then this implies 2, and this is obvious since L is continuous. So if on a dense, if L restricted to a dense subset of X is 0, then you may extend it by continuity. I guess we have somewhere we had it. I guess even here. Yes. Be a dense subset if we have a linear continuous functional, okay, operator, but functional is a special case, then there exists a unique extension to a continuous linear operator. So what does it mean? So if we have a continuous linear functional defined on U, and it is 0 on U, and U is dense in X, then definitely by continuity we have this. Now the opposite direction. So assume U is not dense. This means that if we consider X without the closure of U, this is not the empty set. Hence there exists X0, which belongs to this X without the closure of U. And hence by what? By corollary 521, just the above corollary, there exists L continuous, a linear functional, such that L restricted to U is 0, and L at the point x0 is not 0. And hence 2 is not satisfied. That is, if 1 is true, then 2 is true. If 1 is not true, then 2 is not true. Hence, the following two statements are equivalent. Okay? Agree?
Yes. Yes.
Perfect. Okay, so this is a kind of criterion, so how to check that a set is dense. You may use this property to check that the set is dense. Okay, so these are just some corollaries of Hahn-Banach theorem. And we go further, and we are going to see so another portion of corollaries of Hahn-Banach theorem, which have some geometric interpretation. So let's go further. Oops. The first exercise, home task for you. Let X be a separable norm space. Separable, yeah. Show that there exists a sequence so countably many linear functional, continuous linear functionals on X, such that if we have that for a fixed point X, this condition holds, then this implies that this fixed point X is just the origin. That is, it is enough to have only countably many linear functionals to separate the points.
Dual basis.
Let us not use such words, but you see this separable and here a countable family. Okay, so it's a home task for you to think about. Okay, so now another portion of corollaries of Hahn-Banach theorem, namely geometric Hahn-Banach theorem or separation Hahn-Banach theorem. So what is it all about? So first some definitions. So a subset U of a vector space X is called convex if together with any 2 points of this set also the whole interval connecting them belongs to this set. So it's a convex linear combination of 2 points, that is if I have point X and point Y, so this is the whole interval between these 2 points. Okay, second, let U be a convex set in a vector space X such that this U contains a region and such that for each point X in X there exists a radius, a strictly positive number R, such that alpha X belongs to U already for all alphas between 0 and Rx. Such U is called an absorbing set. So what is it all about? So let me say, so we have U, we have 0, we have a set U. Let me first make U then 0. So this is, but actually no, we don't need, yeah. So this is no, not U. This is 0, 0. This is 0, and this is the set U. Actually, it does not need to be a circle, but nevertheless. So we take any X. We take a straight line. What's going on? Any X. And so if we multiply X with some small alpha, we obtain a point which lies already in U. That is, this means, so either we multiply X with small alpha to put it in U, or we multiply U with this sufficiently big number. So we make, instead of U, we consider U times 1 over alpha, and this is a bigger set which absorbs the given point X. Okay, so such set U as it is drawn in this picture is a nice absorbing set. So everything happens in RD, let's say. But of course there are some other versions. For example, if we have such picture, so probably I start with the circle first. Yeah, and then such picture. It does not want to do what I want. Okay, so if this is my 0, nobody said that that U should be an open set. Probably it's a closed set. So probably my 0 belongs to U. But this is not an absorbing set, because, for example, for such X, you cannot create alpha such that alpha X, for bigger than 0, such that it is absorbed by this set U. So what I wanted to say, this is a bad example. This is a good example. But there are also some other examples which are good, but looking rather as this guy. So it will be the exercise for you. So as the space X, we consider the set of finite sequences. That is sequences let me write down because we have not specified it, such that only finitely xn are non-zero. As a set U in this space, we consider the following set. So the set of sequences in this D such that absolute value of xn is smaller or equal than 1 over n. So D with the supremum norm is a norm space as it is assumed here. So it's a vector space, but also is a norm space. And exercise is that show that U is absorbing but 0 does not belong to the interior of U. So it's not the inner point of U.
So this absorbing property looks like a proper generalization of a open set, because like each open set will be absorbing.
Containing 0, yeah, each open containing 0.
Yes.
Yes.
And so here we want to have this property that we can like tend to 0 along the direction from this set.
I'm not sure that I have understood what you mean.
I'm trying to get some feeling about this property.
Well, but I guess the word absorbing is already saying something. So we want to have a set which can eat any point by just expanding this set.
Yeah, and we see that 0 is not interior, so
here 0 is interior and it's perfect. Here 0 is not in interior and it's bad. But sometimes 0 is not in interior and it's still working. So
yeah. So this
this
is
is the point. So as soon as a set U is such that it contains some neighborhood of 0, everything is perfect.
then it's absorbing.
Yes, but
yes.
Okay, so this is about absorbing sets. Now definition. So let X be a vector space. U is a subspace, a subset, just a subset of X, non-empty. Then we define the so-called Minkowski function or gauge function of the set U. It's a function which is defined as follows. So at a fixed point X, this function evaluated at this point is infimum over all radii, so a positive number, such that X belongs to the RU. So how much we should expand U in order to absorb the point X. Okay? So in order, either we expand U or we, contract our point to the direction of 0. Okay, is the definition clear?
Yeah, so it tells how much do we need to scale our set.
Yes. But
in order to
we have just a set, not necessarily an absorbing set. So probably no matter how big or small R we take, probably we will never absorb a point x. So the functional may take a value infinity.
Okay.
Okay. So lemma, and then this is the exercise, home task. So if U is an absorbing set, then the corresponding Minkowski functional is even a sublinear functional. And furthermore, for all points in interior, so interior points of U, the linear, so the Minkowski functional is takes values smaller than 1. For all points on the boundary of U, the Minkowski functional is equal to 1. And for all points which are in the complement of the closure of U, so exterior points, the Minkowski functional is strictly larger than 1. It is an exercise. Just look at the definition of Minkowski functional and the definition of the absorbing set. Okay. Now theorem, which is the geometric Hahn-Banach theorem. So let X be a norm space over R. We are working only here. So let U and V be two convex sets which are disjunct. In order to make the statement nicer, so let us assume that one of the sets is open. So let for example, U be open. Then there exists a non-trivial linear, continuous linear functional on X, which separates these two sets, these two convex sets. What does mean separates? This means that supremum over all points in one set of this supremum of the values of the functional is smaller or equal than infimum over all values of the functional over all points of the other set. So roughly speaking, we have two convex sets, U and V, and we have a linear functional, L, and there is this hyperplane, so to say, which is the level set of functional, which separates these two sets. Moreover, U is an open set, so it does not contain its boundary. Something like this. Okay, so this is the idea. So with the help of Hahn-Banach theorem, we are able to separate convex sets, roughly speaking. And so the next aim of our lecture is to prove this theorem. So proof, step 1, as usual. Step 1, simple step. We consider the set V, which consists from one point, namely the origin. So what we are going to do, so let A be a point in the set U. It is an open set, which does not contain 0 because we have this assumption. Consider W, which is a shift of U minus A. Then W is convex. Again, you may consider it as an exercise that if we have a convex set and we shift it to a vector, then we again obtain a convex set. If U is an open set, so if we shift an open set, we obtain an open set. So W is open. And now 0 belongs to W. And so W is an open set which contains 0, so it's a nice absorbing set. So W is absorbing. And hence the Minkowski functional of this set is sublinear. By lemma, the lemma was number 25. Note that I take the vector P, which is minus A. P does not belong to W. since 0 does not belong to U. Yeah, because of this condition. 0 does not belong to U, and hence minus A does not belong to W. So let us consider the following subspace, vector subspace. This is just a one-dimensional subspace, which is just a linear span of the vector B. Define a linear functional L0 on x0 as follows. So this is like step two, next step. So we define the linear functional L0 in the following way. L0.
Sorry, can you please clarify the previous moment? So we take so minus A does not belong to W, since 0 does not belong to U.
Yes,
think
so V is just the origin. U is just disjoint with V, so U does not belong, does not have 0. So that's why W does not have 0 minus A.
Okay.
Okay.
Okay, yeah, I see. So we take this V to be just 0.
Yes. So if you would have 0, then 0 minus A is B, and it would be in W.
Yeah, so they will intersect.
Okay, so we define L0 in the following way. This is just T times Minkowski functional of B for any T real number. So all elements of this vector space, we have this form, and on each element we define this functional. Since Minkowski functional is now sublinear because W is absorbing, then everything is fine. Namely, one can check that this L0 is linear, and then it is also continuous because everything happens in one-dimensional space. Is linear and continuous. Moreover, we have that L0 of TB is smaller or equal than Minkowski functional of TB. Yeah, now we use this sublinearity. What does mean sublinearity? I guess we have it somewhere. I guess just to recall U. Yeah, sublinear. A mapping is sublinear if we have this for positive constants and we have triangle inequality. So due to this definition and due to sublinearity of this functional, we have this inequality. So all assumptions of the Hahn-Banach theorem are satisfied. So let me clarify this inequality probably. For T non-negative, L0 of TB is just TPWB, and we use this positive homogeneity. And for T smaller than 0, L0 of TB is less than 0, and PWTB is bigger or equal to 0. Why this? Because this guy is T times PVB. Since so this guy is bigger or equal to 1 since B does not belong to W. and this is and t is smaller than 0. And this is from the lemma. So B is an exterior point for W. That's why they're Minkowski functional. Okay. So B is not in U, but probably on the boundary. So that's why we have here inequality that PW of B is bigger or equal to 1. So I show you the lemma again. So for the boundary equal to 1, for exterior points bigger than 1 for absorbing sets. Okay, so what do we have now? So we have all assumptions of the Hahn-Banach theorem. So we have a subadditive functional, we have a linear function on a subspace which is dominated by a sublinear functional. So we can extend L to a linear function of the whole space, which remains dominated to be dominated by the Minkowski function. But I have to write it down on the next slide. So may I go to the next slide?
Yes.
So by the Hahn-Banach theorem, I guess it is even theorem 510. So we don't need any topology, just a vector structure. There exists a linear functional L defined on the whole X and continuous, satisfying the following conditions. So L restricted to X0 is our L0, and L of X is dominated by the Minkowski functional everywhere in X. Stop. Here we have the algebraic dual. So we have the version of Hahn-Banach theorem, the original version, where we have only vector structure, no norm, nothing, no topology, so no continuity, just linear functionals. Okay. So further, for any X in W, we have that L of X is smaller or equal than PW of X by the construction, but this guy is smaller than 1 by lemma 525. So for inner points, we have this inequality. Moreover, if we consider L of A, using the linearity, it is the same as minus L of minus A. That is, this is minus L of B. That is by definition of, so B belongs to my subspace X0. Hence we know how this L acts on this point. It is just minus PW of B. So B does not belong to W. So this guy is so this guy is then bigger or equal to 1, as we have discussed. Hence, in total, everything is smaller or equal than minus 1. This is by lemma again. Hence, what do we have? for any x in U, which is, I recall that U is A plus W, L of x is equal to L of A plus L of some W. So I recall that A plus big W, it is the set of points A plus small w, where small w is the element of big W. That is, each x from this set has this form. And hence we have this, and hence, so L of A is smaller or equal, L of A is smaller or equal than -1. We have seen it. And L of W is smaller than 1 since W belongs to, it's an interior, belongs to interior of big W. Again, by lemma 525, we have that this stuff, so this L of x is smaller, is smaller than -1 plus 1, that is 0. So what we have achieved for any x in U, L of x is smaller than 0. And L of 0 is 0 because L is a linear functional. Yeah, for all linear functionals, we have this identity. But this identity means that L restricted to V is 0. So this linear functional L has separated two sets, U and V. I recall that V is just this point in our step 1. So we have shown, so in step 1, we have shown everything. So the sets U and V are separated by this linear functional L. But this is not everything, because we want to show that my L is not just linear functional, but also continuous. Yeah, belongs to this space, not only to this space. So it's the next step within this setting. But I need a next slide. So may I go to the next slide?
Just wait
Okay.
10 seconds.
Yes. Again, this follows from this. Oops. What's going on?
Okay, please continue.
Yes. So now we show that that this L which we have constructed is continuous. That is, we show that L belongs to this space, topological dual, not only algebraical dual. So how we show it? Since the set W is open and 0 belongs to this W, hence 0 is an interior point. and hence there exists some positive radius such that the whole open ball around 0 with radius r belongs to this open set W. Since we have constructed L such that on the set W it takes value small or equal to 1, so the same holds also for this open ball. So L restricted to this open ball also takes values small or equal to 1. And now we use the properties of an open ball around 0, that it is not only a convex set, but it is a symmetric set. Namely, from this inequality, we have the following inequality. Absolute value of L restricted to this ball also takes value small or equal to 1. So what has happened? So for any x in this open ball, minus x also belongs to this open ball. And so this absolute value, L of x, it is L of x if L of x is not negative, and minus L of x, which is L of minus x, if L of x is negative. Yes, in both cases, this element, this x and this minus x, they all belong to the same ball. Yeah. So from this inequality, we have this inequality. Agree?
Yes.
Okay, but this means that the norm of L, I recall that this is supremum over all x's in x, such that norm of x is. Okay, I don't want to write it down. I mean, of course, we can. If I have started, okay, let me continue. Absolute value of L of x, and now we may rescale it, that it is supremum over all x's in this BR0 L of x, and here we should, if I'm not wrong, do something like this. So L is continuous. Since we have this inequality, we have also this inequality. Hence, we have shown that L is continuous. Okay, it was step number 1. So for a very specific convex set V, we have shown the statement of the theorem. Agree?
Agree.
So now we consider step 2, general case. Step 2, general case. So consider the set W tilde, which is given by U minus V. What is it? This is the set of all elements U minus V, such that U is an element of U, and V is an element of V. So this set can be represented in the following form. It's a union of the sets U minus V, and the union is taken over all V's in the set V. Okay, then, so you see U is an open set So its shift is again an open set. So we have a union of open sets. So this set is open. V tilde is open as a union of open sets. And moreover, and convex. This is an exercise. So believe me, this is so. Exercise that the set is convex. Moreover, zero element does not belong to the set V tilde, since U and V are disjoint. So in order to obtain zero, I should take vector minus vector itself. Then we will get zero. But this is only possible if there are elements in the intersection. Okay, agree?
Yes, of course.
Okay, by step one, there exists a linear functional, continuous linear functional, such that L restricted to this V tilde is okay, bigger or equal to zero. In our case, we in the step one, we had, so what did we have? Yes, we had even, so we have this. So we have two sets, 0 point origin and another open set. And we have restricted them, separated them by a linear functional L such that for all elements of this open set U, this functional is strictly negative. Of course, if I take minus L, then I get strictly positive functional. So I can take, so this is my new U. This is an open set which does not contain zero. So we can separate zero and this open set by a linear functional such that this holds, or even this holds. And as I said, I have just changed the sign. So in the step one, we had this, but it does not matter. Okay, so, but what does mean that L of U minus V is bigger or equal to zero for any U in the space U and any V not in the space, in the set U and in the set V. This means nothing else but the statement that LU is bigger or equal than LV for all U's in U and all V's in V. But this is exactly what we wanted, namely that infimum L of x in U is bigger or equal than supremum of x over in V, L of x. That's it. Okay, are there any questions? Seemingly no. So let us go further. Yes, may I go further?
Yes, please.
Perfect. So corollary. So let X be a norm space over R. V be a convex and closed. A is a point which is not in this set V. Then there exists a non-trivial continuous linear functional on X, which separates the closed convex set and the point in this strict way. So proof is very short, that's why let us prove it. So V is closed. Hence, its complement is open, and A belongs to its complement. Hence, there exists a radius, strictly positive radius, such that the point A lives in this V complement together with the whole ball. So consider U, which is an open set, BR of A. So we have then, so V is a closed set, and this is an open set U, such that U intersected with V is an empty set. So we may apply the separation theorem, Hahn-Banach separation theorem. So by theorem 526, there exists a linear and continuous linear function, continuous linear functional L on X, such that supremum of L of X over V is smaller or equal than infimum L of X. Now let us check that we may have this. So strict inequality, but here not infimum over the whole ball, but just the value of the functional at the centrum of the ball. So case 1, A is just the origin. Hence, L of A is just the L of 0, and this is by, it should be 0 because L is a linear functional. But infimum over all X in this open ball by R over A, now A is 0. This infimum should be smaller than 0, since otherwise L is identity. Why it is so? Because L is linear, and this open ball, PR0, is absorbing. That is, at the centrum of the ball, L is 0. L at this point is 0. So we claim that infimum is smaller than 0 because if it is 0, yeah, it cannot be bigger than 0 because we have already this value. So if infimum is 0 and the set is absorbing, this means that actually infimum over the whole space is 0, but we have a linear functional, which is, so to say, bounded from below. This is only possible in this case. Okay.
Could you please repeat again?
Okay, so in the centrum of the ball, we have this bilinearity of L. So this means that infimum is like this. It cannot be positive. It is either 0 or smaller than 0. So the claim is that infimum is smaller than 0. Because if infimum is just identically zero, what does it mean? Using the linearity of this functional and using the fact that the ball is absorbing. So if infimum over all x's in this ball, L of x is just zero, hence infimum over all x in our space, L of x is also zero. I just use that we can absorb any point x by the set. So we just rescale this open ball to get any bigger ball, yes? And using the linearity of L, I obtain the same. But this means that we have a linear functional which is bounded from below. Or you may also consider such thing and say, okay, that not only infimum is equal to zero, but also supremum of this functional is equal to zero due to linearity and due to symmetry of this ball. So in both considerations, we obtain that the functional is identically zero. So linear function which is bounded from below is zero.
This time is okay. Thank you.
Okay. So it was case one. Let me write down case two just here. Case two, we reduce it to reduce to case one by translation and linearity. So use linearity of L. So translate everything, shift everything to zero so that we separate not U and V, but the shifted sets such that the shifted center of the ball is in zero. Okay, we are not going to go further in the details, but just pay attention that if we have a linear functional, then its supremum over an open set, supremum and infimum is taken on the boundary, not inside. So as it was presented here. Convex. If we have a convex set, yes, for convex set, for any convex set, supremum of a convex set or infimum of a convex set, they are taken on the boundary of the set. The boundary may belong to this set or not, but nevertheless. Okay, so one more corollary, or this is what we have proved, sorry, so we have proved it. Yeah, so one more theorem, which we are not going to prove, but still it's a kind of nice result. So let X be a Banach space, V be a bounded closed convex set. The statement is that the set of all continuous linear functionals that attain their maximum on V, that is supremum is attained, and then it is maximum, not only supremum. So the set of all such functionals is dense in this space. That is for, so to say, in much cases, the minimization or the optimization problem for linear functionals over convex sets is a well-posed problem. Okay, this all follows from the Hahn-Banach theorem. So this theorem you can find the proof in this paper. So summary. So we have this Hahn-Banach theorem. So the first statement is just the statement which uses the linear structure of the space, nothing else. Then we have, in the case of norm space, we obtain the Hahn-Banach theorem about the continuous extension. That is, if we have a continuous linear functional on a subspace, we may extend it up to a continuous linear functional on the whole space. And one more important result is the separation Hahn-Banach theorem or geometric Hahn-Banach theorem, which says that using continuous linear functionals, we may separate convex sets. So if one of the sets is open, then this separation looks like this, and it's very nice. So the other corollary is also, just to present that we may do it more rigorous, so to say. That is, here we have this inequality. There are of course many other versions of this separation theorem, more finer versions, but of course we have no time and no reason to discuss all the versions and all the generalizations. How fine, in which cases we may separate the sets depending on the properties of the sets. Okay, so it's a kind of hint that convex optimization, it's a theory which has, it's a rich theory which has a lot of results. Everything works finer than just if you optimize some function over just a set, not convex. In particular, the questions about L-poseness of the problem are solved in a better way for convex optimization. Okay, that's it with the chapter 5, and I have some time to start chapter 6. This is what I wanted to start. This is about dual and bidual spaces, and of course, to have good properties of these spaces, we often to show good properties of these spaces, we often need to use this Hahn-Banach theorem. So the Hahn-Banach theorem is really a fundamental result, which has a lot of consequences in further chapters, so to say. Okay, so a small pause to realize that we have finished chapter 5 and we start something new. Okay. Prelude. So let X be a norm space, again over R over C. I recall that the space of all continuous linear functionals is denoted by X star, where star is like a snowflake. So X star, and it is called the topological dual space. So usually I just say dual space because we mainly work with topological dual. We have already discussed that this space is a norm space with a norm of linear functional. This is the definition of the norm of a linear functional given here. And this is a norm, so this guy is a norm space. Moreover, this is a complete norm space. That is, this is a Banach space, and it follows from theorem 410. So this was this theorem 410. So let X be a norm space, and let Y be a Banach space. Then the space of all continuous linear operators from X to Y is a Banach space. That is, it is complete. In particular, if we consider topological dual, it is the space of all linear, so to say, operators from X to K. And K is a Banach space. It's a field R or C. That's why for any norm space, its topological dual is complete. Okay, so let's say we have started with some space X, we have considered its dual, and it is a Banach space. So now let us start from this Banach space and do the same. Yes? definition. So the space X with two stars, which is the topological dual to this Banach space. This is the space of all continuous linear functionals from X star to K. And this space is called the bidual space of X. Okay. So by theorem 410, which we have just seen, this is again a Banach space with the norm of linear functional. But now our elements are linear functionals on this space. So this norm is given as supremum over all absolute values of L stars evaluated at point L, element of this space. And we take supremum over the closed unit ball around 0 in this space. So this is a standard definition of a norm of linear functional. We just insert the spaces on which we are working. Okay. First of all, is everything clear so far?
Yes.
Perfect. Now we need to recall some notions. So remark, so let x1 with d1 and x2 with d2 be two metric spaces. A mapping J from x1 to x2 with the property that it preserves distances, that for any 2 points in x1, the distance between their images is the same as the original distance between the points. So a mapping which preserves distances is called isometry from x1 to x2. And since this mapping preserves distances, so any isometry is always injective. If this isometry is even bijective, that is not only injective but also surjective, then this J is called isometric isomorphism. And if J is not surjective, that is only injective and preserves distances. If J is not surjective, then J is also called isometric embedding. So by saying isometry, I do not specify, I do not distinguish if the mapping is surjective or not. And by saying this or that, I specify if the mapping is not only isometry, but surjective or not. Okay, so we have discussed this. One more point to discuss. For each x in X, consider the following mapping. J with index X, it's a mapping from X star to the field of numbers, which is just the point evaluation. So we fix a point X in X, and we consider this mapping, which just take any continuous linear functional L from this space and evaluate this continuous linear function at the point X. Then the statement is that this mapping, it is a linear mapping. I hope it is obvious that this is a linear mapping. Moreover, this is a continuous mapping because so this mapping gx at the point L, absolute value, by definition, it is just absolute value of L of x. And then this is the standard inequality that this is smaller or equal than the norm of L, the norm of the linear functional L, times the norm of x. Hence, you can see that this mapping is a bounded linear mapping, and hence continuous. And hence, this guy, since it is a linear and continuous functional from x star to k, this is an element of the bidual. So for any element x in X, I have created the element which belongs to its bidual, and it works as a point evaluation of a linear functional at the given point X. Everything is clear?
Yes.
theorem. This mapping, so I guess I have, yes, this is written now. Now I may consider the following mapping. This is the so-called canonical mapping, so canonical embedding of the norm space X into its bidual. And this canonical mapping works as follows. I take any element X in this space and associate to it this mapping Gx, which is a point of evaluation in this point X. So this canonical mapping, it is an embedding of X into X star, and it is a linear isometric embedding. So it is isometry and even a linear mapping, and it works as follows. Now we have to prove it. I guess we still have some time. Let us do it. Linearity is obvious. If no, then it is exercise. Now to show that it is isometric embedding. So by corollary 519, I guess I'm still able to show it. We have discussed it today. Yes, corollary 519. So the norm of X is given, for example, like this. So it's a dual picture. We have this, and we also have this. So by this corollary, so let us calculate the norm of this element of the space X2 star. So it is, by definition of the norm of linear functional supremum over all L in this space X star, whose norm is small or equal to 1. And I take evaluations of this functional on points of this space X star. So this is just definition of a norm of linear functional for linear functional which is living here. Now I use the definition of this linear functional, just insert what is it. This is just L of X. So this is absolute value of L of X. And now here I use this corollary. This goes here. This is just the norm of X in X. So you see we have an isometry. Okay.
Nice proof.
Ah? Sorry?
I just say nice proof.
Okay. Good. Okay. So please pay attention. So this is the canonical mapping. It works exactly like this. And some consequences of this theorem. Corollary. Each norm space X possesses a unique completion up to a Banach space. So the proof is one line, but before I would like to clarify what does mean completion. So it is written in blue. So for a metric space XD, any couple X hat, D hat, and J, where X hat, D hat is a complete metric space, and J is an isometry So J maps X to X hat, original metric space to the complete metric space, and it is an isometry such that the image of the original set X under this isometry is dense in this new complete space X hat. So any such couple, so once again, any couple is called a completion of X. So for any metric space, its completion is unique up to an isometric isomorphism. That is, of course, there are many couples of this type which produce a completion, but they all are isometrically isomorphic to each other. So now we have a norm space X, and what is this couple? So J is like here. So J maps X into X double stars, and we know that this is a Banach space. So if we consider J of X and its closure, then we obtain a closed subspace of a Banach space. That is, this is a Banach space itself, and of course, J of X is a dense subset of its closure. So this is a construction. So this is the guy which provides a completion of a norm space. So once again, how to get a completion of a metric space? For example, we have rational numbers, then we complete it and we obtain real numbers. So how did we do it? We have taken all Cauchy sequences in Q and added their limits to Q, and then we have obtained R. But in order to add the limits of all Cauchy sequences, yes, for getting a complete space, we should have them in advance. We should have the objects which we want to add. So in this case, we know that we have R, and we take these limits from this space. But in an abstract space, in an abstract situation, we have just a metric space of some objects, and one has to create these limits of Cauchy sequence somehow. We should have these objects. So this is one of the ways to have this object. Yeah. So we take them from this guy. So this is the idea. Okay, everything is clear.
Yeah, it's clear.
Perfect. Now let us discuss this canonical mapping in a more careful way. So the canonical mapping, it is isometry and hence injective, but it does not need to be surjective, even if X itself is already a Banach space. So even if X, so we know that this guy is Banach space. This guy, even if this guy is a Banach space, we cannot promise that this mapping will be an isometrical isomorphismus, namely that the isometry is surjective. This leads to the following definition. So a Banach space is called reflexive if the canonical mapping, so exactly this one, if the canonical mapping is surjective and hence isometric isomorphismus. So this is a definition which is important of definition of reflexive spaces. So only Banach spaces have chance to be reflexive. If we consider a normed space which is not complete, then there will be no chance that such a mapping will be surjective. So incomplete normed spaces have no chances to be reflexive. Okay, is it clear?
Yeah, I think it's clear.
Perfect. So, one more remark. There exist Banach spaces X which are isometrically isomorphic to X double stars, so to its bidual, but with the use of some other isometric isomorphisms. But it may happen that their canonical mapping, so exactly this mapping, is not surjective. That is, so we have the situation when X is isometrically isomorph to X star, but X is not reflexive, because for being reflexive, it is not enough. For being reflexive, this should be done by this exact J, by this canonical mapping. Not by some isometric isomorphism, but by exactly this one. Okay, so there are counterexamples. Counterexamples can be found by the keyword James space, and I recommend you this book, Topics in Banach Space Theory, where you can read about James spaces and also more deeper presentation of some topics in Banach space theory. Okay, I guess it is, yeah, so we can say a little bit more that in the case of finite dimensional norm spaces, they are, of course, always closed, and they are always, so complete, closed, complete, and they are always reflexive. And we have this identity, which is known even from linear algebra. All linear functionals are continuous in this finite dimensional setting, and everything is totally fine. What happens in general, this we will discuss next time. I guess this is a nice time to stop, even here. So be careful with all definitions. Please understand them properly. Okay, are there any questions or comments? Let me write down. Like this. Okay, seemingly there are no questions, so I stop the recording.